In today's session, we'll be looking at what is Hill Cipher, and I have put up the photograph of the inventor of Hill Cipher. So, Hill Cipher was developed by the mathematician Lester Hill in 1929. So, this encryption algorithm takes m successive plain text letters and substitutes them for m ciphertext letters. Say, if your plain text is Satish, then what this algorithm supports is you can take m consecutive or successive plain text letters and substitute them with m. Say if these are ciphertext letters, for instance, we can substitute them with m ciphertext letters. So far in the previous algorithms like Caesar cipher and Playfair cipher, we were able to take either one of the letter and substitute that with another ciphertext letter, or take maximum two letters and substitute them with two ciphertext letters. But here, there is no restriction. You can take m successive letters and substitute them with m ciphertext letters. So let's go to the algorithm. Let's take a look at step one. Step one is, as usual, we have to select a message to encrypt. So I'm taking this message Satish. As I told you, we can take m plain text letters and substitute them with m ciphertext letters. Here, for a demonstration, we'll have m is equal to 2. That is, we'll take two plain text letters and substitute them with two ciphertext letters. So our value for m is 2 here. So I'm going to divide this input message as two characters each, because we're going to take two characters and substitute them with ciphertext characters. Whereas here you see the last character is alone, it's not having another character. So it's not becoming a digraph here. So for this, what we can do is we can pad another character. So this character can be anything. Here we are using A. So now we can take two characters at a time and then encrypt as ciphertext. So that is a step one. We'll go to step two. We have to select a key. So here there is a strategy for selecting a key. The key is a square matrix. It can be either a 2 cross 2 square matrix when m is equal to 2. So when you're going to take three consecutive letters, that is when m is equal to 3, you should find a 3 cross 3 square matrix. So your key should be the size of a 2 cross 2 square matrix when you're going to take two characters, and it should be the size of a 3 cross 3 square matrix when you're going to take three characters at a time and convert it. So the size of a key depends on the number of characters you're going to take at a time to encrypt. So here, since we are going to take two characters at a time, our size of the key should be 2 cross 2, that is 4 characters. That's what is given here. If we encrypt two letters at a time, then the key size is 4, because 4 can form a 2 cross 2 square matrix. That's the catch. If you have the length to be 4, we can convert the key into a 2 cross 2 square matrix. If we encrypt three letters, if we take three characters at a time and convert that to ciphertext, then the length of your key should be 6 letters and so on. And the key that we have selected is DBGF. We have selected a key of length 4 because we'll be able to convert this into a square matrix, that is a 2 cross 2 square matrix. So the key that we are going to use in our algorithm is DBGF. Step 3, we are going to assign a numerical equivalent to each letter. This we have done with many other ciphers like Caesar cipher. We are going to take all the alphabets of the English language and assign them a numerical value. This value will be incremented by 1 each time till we reach the end. So we'll have 25 to be the value for Z. The next step is step number 4. We are going to convert this key DBGF into a 2 cross 2 square matrix, and this is how it's converted into a 2 cross 2 square matrix. We're going to write it as DBGF, but we'll not be able to use DBGF in our computations. We have to convert these things to numerical values. For that, we'll be using our table, and this is the table that will help us in this conversion. So what is the value for D? D it is 3. What is the value for B? B it is 1. So it will be 3, 1. The value for G is 6 and the value for F is 5. So this 2 cross 2 matrix with alphabets will be converted to a numerical equivalent like this. So the key that we are going to use is, that is the key K that we are going to use is 3165. So our key is finally done. This is the key that we'll be using in our encryption. Next step is we have to take this input message that has been padded with an A at the end. We have to convert that to an n component vector. Here n is 2, n is equal to 2 because we are going to take two characters and convert that to a component vector. Let's see how we convert this message to a component vector here. So this is the message. We split that as two characters each, and this will be converted to a component vector like this. This is a component vector where n is equal to 2. Likewise, SA, TH, this is another vector, IS, another vector, HA is another vector. So we take this message and we convert that into a component vector of the size. The size is equal to the number of characters we are going to encrypt at a time. And again, we cannot use these values like this in our calculations because these are alphabets. We need to convert them to numerical equivalents. For that, we'll be using this table. So what is S and A? S is 18 and A is 0. So this will be changed as 18 and 0. See, that is the equivalent of this. Like that, T and H. What is T? T is 19. And what is H? H is 7. So you just go and find the equivalents, and this is called the plain text P. So we take every component vector and we multiply that with the key, and we'll be denoting this component vector as P. And you can call this P1, P2, P3, P4 if you wanted to. Next, we'll take a look at the encryption algebraic expression, that is a ciphertext can be attained by multiplying the key with this plain text, that is nothing but this component vector we have created, right? Each containing two numbers, so it can be any two numbers 18 and 0. So we're going to take the key and start multiplying that with the component vectors. Mod 26 is the number of characters, that is from A to C. So we have the key, this is K, and we have to multiply that with the component vector which we have arrived at in the previous slide. So this is P1, and we have to finally get this result and we have to perform a mod 26. So how this multiplication is done, you take 3 and multiply it with 18. So 3 star 18 plus you take 1, you multiply that with 0, 1 star 0. So what is the result of this? This will be 54. Likewise, you take the second row 6 and you multiply that with 18. So it is 6 star 18 plus you take 5 and then you multiply that with 0. So what is the result of this? This will be 108. So multiplication of the key with the component vector leads to another component vector of size 2, and we have to perform mod 26 of this. So how will you perform mod 26? It's nothing but 54 mod 26. 54 mod 26 is 2. The remainder is 2 when you divide 54 by 26, and 108 mod 26, the remainder is 4. So we have arrived at the result for a computation. Now we can convert 2 and 4 to alphabets by looking at a table again. So this table, what is the equivalent to 2 here? 2 is nothing but equivalent to 2 is C, and what is the equivalent to 4? 4 is E. And what we have taken as input 18, 18 is nothing but S, and A 0 is A. So this is the plain text SA which has been converted to ciphertext CE. So we have converted one pair of plain text to ciphertext. And now we have to repeat this process. We have to take the next two characters, that is T and H, and their equivalents. We have to multiply that with the key, perform a mod 26 to get the ciphertext out. Let's repeat the process now. Let's now take This is P2, right? So this is corresponding to the value T and H in the plain text. And we have to multiply this. How will you multiply this? It's very simple. You take 3, you multiply with 19. So it is 3 into 19 plus you take 1, you multiply that with 7. So 1 into 7. So what is the output of this? This will be 64. Likewise, you go to the second row, 6 into 90 plus what is this? 5 into 7. What will be the output of this? This will be 149. So once when you are done with this, what next you have to do? We have to perform mod 26. What is 64 mod 26? The remainder will be 12. What is 149 mod 26? The remainder will be 19. So we have arrived at a result. Now we have to find the equivalent alphabets for 12 and 19. For 12, what is the equivalent alphabet we have? This is M. For 19, it is T. So the ciphertext corresponding to T and H is M and T. Like that, we have to repeat our process for P3 and P4 too. Now we take the key. Let's go to P3, that is 8 and 18. So this is corresponding to I and S in the plain text. And let's do a multiplication again. That is 3 into 8 plus 1 into 18. So what is the value that we are going to get here is 42. Likewise, you take 6 into 8 plus 5 into 18. So what is the value we are going to get here is 138. So once when you are done with this, what we have to do next? We have to find mod 26. So 42 mod 26 is nothing but 16 and 138 mod 26 is 8. So we arrived at 16 and 8. What is the ciphertext corresponding to these values? 16 in this table, 16 is Q, and what is 8? 8 is I. So the ciphertext equivalents of I and S is Q and I. Is that clear? So you have to be very careful with the computations. If you make something wrong here, then your entire computation becomes wrong, and your results also will be wrong. So this is again a problem with this cipher technique. You have to do a lot of mathematical calculations by hand, and something goes wrong, it's going to be the end result will also be wrong. Can we take P4, the last component vector? Okay, now let's take the key and multiply that with the last component vector P4. So this is corresponding to H and A. So now we have understood why we padded this message with an A, because A is corresponding to 0, so our computation becomes a little easy. So will you multiply this? This is nothing but 3 into 7 plus 1 into 0, that is 0. So you'll have 21. Likewise, 6 into 7 plus 5 into 0, that is 0. So you'll have 42. So once when you have found the result, what next? You should never forget to do a mod 26. So when you perform a mod 26, the output is going to be 21 mod 26 is 21 and 42 mod 26 is 16. So this is our result, and we have to find the equivalent alphabets. For 21, what is the equivalent alphabet? V. And 16, what is the equivalent alphabet? Q. So for H and A, the corresponding ciphertexts are V and Q. So this message, plain text message SATHISHA, has been encrypted to the ciphertext CEMTQIVQ. So that is our ciphertext. I hope you are all clear with how we perform encryption using Hill Cipher. The next strategy that we have to understand is how we can decrypt using Hill Cipher. So we are going to take this ciphertext we have generated in a previous slide and convert that to plain text. And decryption involves a little more computation than encryption. We'll see that why. For getting the plain text, we have to multiply the inverse of the key. with the ciphertext component vector mod 26. So what is this inverse of the key? It's nothing but the inverse of a matrix. We all know that K is a matrix. It's a 2 cross 2 matrix, right? So we have four numbers here. And now we need to find the inverse of the matrix. So this is the formula for finding the inverse of the matrix. It is nothing but 1 by determinant of K into adjoint of K. We're going to use this strategy to find the inverse, and then we'll substitute that inverse in our algebraic expression to compute the plain text. First, we look at how to compute this part 1 by K, 1 by the determinant. So now let us take a look at how to compute 1 by the determinant, that is K. So we have the matrix K is given here, and now we have to compute this determinant K. How to compute this is just multiply the diagonals, that is 3 into 5, and this diagonal, that is 6 into 1, and you subtract it. So it is 3 into 5 minus 1 into 6. The result should be non-zero. So here we are getting 9, it is fine. But if you get K to be a 0, if K is equal to 0, then there's something very wrong with our key. We cannot go ahead with our decryption, because when K is equal to 0, there is nothing defined for 1 by 0. We cannot divide 1 by 0. So when this part is undefined, your decryption process halts. You cannot go and decrypt. So you cannot select a key like this. For instance, you cannot have a key like 2, 2, 2, 2. So this is nothing but 2 cross 2 minus 2 cross 2. So your K will be 0. So your decryption cannot happen. Your algorithm will not work. So this is a very important thing. So that's why I've given here. The value of K should not be 0 when you compute this determinant. So this kind of a decision should be taken even before the encryption process while you're selecting the key. Can very well convert that to a numerical equivalent and check it out right there, rather than ending up with a problem like this in the later on stages. So our result is a 9 here, so it's not a 0, so we are not having this issue. So what we have computed now is, it is nothing but 1 by the determinant, that is 1 by 9. The next thing that we have to compute is the multiplicative inverse. So what is this multiplicative inverse? We should take this 9 and we should find the multiplicative inverse x with respect to mod 26 such that the result is 1. We have looked a lot at multiplicative inverses. I put up a separate lecture on how to find multiplicative inverses. If you're not clear with how to find a multiplicative inverse, please refer to that lecture. So here we have found the determinant. We need to find the multiplicative inverse of this determinant with respect to mod 26. So we can go with some trial and error here. 9 into 1 mod 26. That is 9 mod 26 is 9. So it is not, 1 is not the multiplicative inverse. 9 into 2 mod 26. That is 18 mod 26 is 18. Again 2 is not the multiplicative inverse. 9 into 3 mod 26. So 9 into 3 is 27 mod 26. So 27 mod 26 will be equal to 1, right? So 1 is equal to 1 here. So the multiplicative inverse here is 3. So again, a definition from our multiplicative inverse concept. When will you have a multiplicative inverse in modular arithmetic? Only when these two numbers have a GCD of 1. Do you remember that? Say when you want to find the multiplicative inverse of AX mod B is equal to 1, and if X is the multiplicative inverse, we can find the multiplicative inverse only when the GCD, the GCD of A and B is equal to 1. Is that clear? So when an multiplicative inverse will exist for this? Only when the GCD of 9 and 26 should be 1. So this is very important. GCD of 9 comma 26 should be 1. If Say you have determined k to be 8 and you're trying to find the multiplicative inverse like this, that is 8x mod 26. Say our k value is 8. Now we have common factors for 8 and 26 and the GCD is not 1. So your x, you can never find an x. Again, you'll not be able to proceed further with your algorithm. Your matrix is not invertible. So these two decisions are very important while you're selecting your key. That is, you should have the multiplicative inverse for your determinant. So these are some of the choices you have to make in the very beginning of your key selection. And I didn't tell you during that time to avoid all that confusion. But if you don't follow these rules and you select a key wherein the GCD of that determinant and 26 is not equal to 1, then your matrix will not be invertible and your decryption will not happen. Likewise, your determinant should not also be equal to 0. Then in that case, again, your matrix is not invertible. So we have finished computing 1 by the determinant. So we finished computing this. The result here is nothing but 3. We know that. Now we have to compute adjoint of k. What is adjoint of k? It is nothing but you have this key here and you're going to just interchange these two values as 5 and 3. You just interchange these two values and then you change the sign of these two values. So these two values will be negative numbers now. So it is -1 and -6. So this is nothing but the adjoint of k. So you have k. How will you find the adjoint of k? Just interchange these two numbers, change the sign here. That is the adjoint. So we know what is this. This is nothing but 3 and we know what is the adjoint of k from our previous slide. So this we have computed and we have computed adjoint of k. Now we'll multiply adjoint of k with 1 by k and what will be the result? This is nothing but 3 into 5, 15 minus 3 minus 18, 9. Okay, so all this computation we are performing to find k inverse. Still we are not done with the computation with k inverse. There's one more step remaining. Since we have negative numbers here, whenever you have a negative number you just add that with a 26 to avoid the negative number. Say I'm just going to do add that with the 26 here. So what will be the result? 15, 26 plus minus 3 will be 23 and 18 minus 18 plus 26 will be an 8 and 9. So finally we have achieved our k inverse, that is 15, 23, 8 and 9. So just to remove the negative numbers we were adding a 26 with the negative numbers alone. So our k inverse is done. The next thing is we have to go in for decryption. So what is the algebraic expression for decryption? It's nothing but you get the plain text by multiplying k inverse with the n component vector of the ciphertext mod 26. So what is k inverse? K inverse we have found it, that was from a previous slide. And what is the C? So we have achieved the ciphertext right from our encryption. You remember CEMTQIVQ. So this ciphertext was achieved by encrypting the plain text Satish A. And how did we achieve this ciphertext? CEMTQIVQ. So this ciphertext was achieved by encrypting this plain text. And now we have to take two characters in the ciphertext and make it a component vector like this. So CEMTQIVQ. And you represent this ciphertext as a number equivalent to be useful in our computations. So what is CE? That is nothing but 2 and 4. So you change it. CE is 2 and 4, MT is 12 and 19, QI is 16 and 8, VQ is 21 and 16. So you convert these vectors to number equivalents using a table. So this is called the ciphertext C. You can say this is C1, C2, C3, C4. So what is our decryption? It is nothing but K inverse into C mod 26. We know what is K inverse, what is C. So we're going to take this K inverse and multiply that with C1 and we do a mod 26. So like that we have to repeat this process. So after this computation we'll take K inverse, multiply that with C2, K inverse, multiply that with C3 like that to get a plain text. Let's finish this computation. So how will you compute the result here? Is nothing but 15 into 2 plus 23 into 4. The result is 122. So now let's go to the second row and multiply it here. So it is 8 into 2 plus 9 into 4. So what is this result? This is nothing but 52. So once when you found these two numbers, this vector, you have to perform a mod 26. So what is 122 mod 26? That is nothing but 122 mod 26, the remainder is 18. 52 mod 26, 26 into 2 is 52, so the remainder is 0. So we have attained a result. We have to go to this table, find the alphabet equivalent for 18. For 18, the alphabet equivalent is yes. For 0, what is the equivalent alphabet? It is A. So we have achieved our first pair of plain text message. So for 2 and 4 corresponding to C and E, the ciphertext has been decrypted to the plain text S and A. Now we have to repeat the process. So let's go and take the inverse of the key and then multiply that with 12 and 19. This is nothing but C2 and perform a mod 26. So what is this? This is nothing but 15 into 12 plus 23 into 19. The result here will be 617. Likewise, you take 8 into 12 plus 9 into 19. The result here is 267. So once when you get this result, this is again a vector. You perform a mod 26. So what is 617 mod 26? It is 19. And what is 267 mod 26? It is 7. You find the equivalent alphabets. For 19 it is T and for 7 it is H. Can take a look at the table. This is what is the ciphertext. Now let us go and perform the same thing. We take the inverse and then we multiply that with C3 and then we have to perform a mod 26 with the result. So what is the result here? It's 15 into 16 plus 23 into 8. So this is equivalent to 424 and 8 into 16 plus 9 into 8, that is equivalent to 200. So on this result we have to perform mod 26. What is 424 mod 26? It is 8. And what is 200 mod 26? It's 18. Now you find the corresponding alphabets. For 8 it is I and for 18 the output is S. So for these two ciphertext characters, our corresponding plain text is I and S. Let's go to the next computation. So again we take the key, we just compute that with C4, the ciphertext vector C4, and we perform a mod 26. This is nothing but 15 into 21 plus 23 into 16, that is equal to 683. And likewise 8 into 21 plus 9 into 16, that is equal to 312. Now you perform a mod 26 on this. So that 683 mod 26 is 7, the remainder is 7. 312 mod 26 is 0. The corresponding alphabets for 7 and 0 is H and A. So we have retrieved our final pair of plain text. So finally, we have achieved our decryption. So finally, we have achieved our decryption. We have taken this ciphertext CEMTQIVQ, and then we have converted that to plain text SATHISHA. So our decryption is done. So let us conclude Hill Cipher. I hope you all have understood how encryption and decryption is performed using Hill Cipher. The very important thing that you have to consider in Hill Cipher is the determinant for your key should not be 0. If the determinant for your key is a 0, you have to opt for some other key such that the determinant is not 0. The next important thing that you have to consider is the determinant, the value of the determinant, along with the number of alphabets, that is 26 alphabets you have taken, the GCD should be equal to 1. Only then you'll be able to find this multiplicative inverse. If your determinant is something that is with respect to 26, if the GCD is not equal to 1, then your matrix is not invertible. So these two decisions you have to take up in the very beginning. Whenever you select a key, check what is the value of the determinant. Check whether the determinant has a GCD of 1 with the number of alphabets you're going to use. So if the number of alphabets you're going to use is 26, then the GCD of the determinant with the number of alphabets should be equal to 1. Then only your matrix will be invertible. And the basic Hill cipher is vulnerable to a plain text attack. That is, if an opponent knows a combination of plain text and ciphertext pairs, he can very well solve that easily. So that's what they say. An opponent who intercepts n plain text and ciphertext character pairs can set up a linear system which can usually be easily solved. So whatever Hill cipher that we have seen now is vulnerable to a known plain text attack. So with that, let us conclude our discussion on Hill ciphers. Hope you have understood this. Thank you.